Hello, everyone. So I would like to first thank the SPT for inviting me here. It's really a great event, and this DSPT team, as Eliano said, is doing a really good job, not only today, but all the activities and the initiatives that have happened in the past are really amazing. So my talk is very different from the previous one. So I'm going to talk about something that is a bit, perhaps at a more philosophical level, if you like. So it is about what is boosting AI. So AI is having a really great time now. We are having a revolution that is being brought mainly by companies. Companies are driving AI right now, although AI has been around for many years. And we can ask what made the difference, and that's basically what I'm trying to answer here, ask and answer with your help, perhaps. So, and I will also talk a little bit about what can go wrong with the present moment of AI. So, I learned AI, I started learning AI in 1987. You remember that year, maybe many of you were not even born, but 1987 was a great year, and that was my first contact with artificial intelligence. What was artificial intelligence at the time? It was Prolog, Lisp. Okay, I loved Prolog, I hated Lisp. Prolog is great. I worked with Prolog for many years. I'm teaching Prolog right now, currently at the Faculty of Science. And I really like it, but the first thing I ask students when they come, I say, this is not a mandatory course. Why are you learning Prolog? Do you see any job asking for Prolog programmers? But we always have 40, 50 people doing that. And I think that Prolog is really important and can be more important in the future. Actually, very recently, I was talking to someone from ING, the big bank, and I was surprised that he was telling me that they are now using Prolog in the bank for certain processes. But it is certainly out of the mainstream of AI. So it was about planning, A*, frames, scripts, knowledge representation. Expert systems were a big thing. There were great hopes, which would, there would be some disappointment following short after. And at halftime, AI was losing, okay? So there's another analogy here, if you can check. A second AI winter followed, and it was not so fun. And it was halftime because more or less 30 years before, 30-something years before, AI was sort of starting. And we are now 30-something years after 1987, which was my start in AI. So Alan Turing was asking, can machines think? This was an important question and still is. There was a Turing test, the imitation game that was proposed by Turing. There was some interesting developments like John Searle's Chinese room. And the Turing test these days is something that we can make when we talk to a chatbot or we use automatic translation. It is challenging to sometimes to tell if it is a human or not. So AI is now in many tasks passing the Turing test for very focused things. Artificial intelligence as a term was coined in 1955 by McCarthy and Minsky. And short before that, there was a computer predicting the victory of Eisenhower in the US presidential elections. And we had a TV host talking to the computer. So there was this interaction with the artificial intelligence. A very interesting point in the history of AI is the coining of machine learning. Arthur Samuel started working with a program that would play checkers. And there was a very important development that was very recently sort of mimicked in Alpha 0, is that in order to make the program play well, not only the program didn't have any kind of strategic notion of how to play, there was only the the definition of rules of the game, but the machine was playing against itself for a very large number of times. And since machines have a lot of patience, a lot of time, it would spare the time of experts. And this is very important. So humans are usually and are frequently the most expensive part in the AI development loop. So taking humans out of the loop is important to make the process faster and to make AI develop faster. But be aware, we cannot take humans out of the loop. That is very dangerous. And we are going to talk about that later. So there were other things like data mining that appeared in the 80s and in the 90s and at the end of the 80s. And this was a very important moment for AI because we had, for the first time, companies driving AI in big numbers. Because companies had data from their databases, and these databases were sitting there and they had to be developed and they had to be explored. There was knowledge. People had this notion that there was knowledge that had to be explored and it had value. So since then, data mining and artificial intelligence has moved to a problem-driven discipline and still in many aspects very much human-dependent, with some exceptions. But basically, databases were designed by humans. The data fields were human palatable, so they had to make sense to humans. They were human readable. Data science then appeared as an overall term, big data, etc. But what we had was already going. So there was a sort of parallel story with the connectionism, neural networks appearing with the perceptron, with backpropagation that was actually invented by an European, although all these guys here are Americans. But it was made popular by Americans and Canadians mostly, and then more recently with the deep learning developments that were part of this big revolution of artificial intelligence. So what now? So there is this AI spring that we are living and that is motivating events like this. So this is part of the AI spring. This is happening, and we have here 400 people because we are in the AI spring. So something happened, something really different happened. So, of course, data is very important. All the data that we have available, mostly since the 90s, boosted AI. So the corporate information systems, which are permanently collecting data, web and Web 2.0, IoT with the sensors, all this information, and in a great respect, the web with the big companies that work on the web that can collect lots of data, textual data, image data, social data, that can make the difference. This has made AI move from a model-based perspective to a data-driven model. Of course, computing power. We have the Moore's law, which is, some say, well and alive. Others don't agree with this opinion. Others even scare us with the possibility of a singularity that can bring the superintelligence that will kill us all. But this is something that is very important also for the boosting of AI. But there's something else, and that is this something else that I'm going to focus on now that I think is very important, that has been very important for the boosting of AI. So, for example, if we wanted to build a classifier in the old days, we had a situation like this. We had trains going east and trains going west, if you know this very classical problem of classification. So we had to design features, and humans had to design features, and there was a very heavy, intensive task for the humans to do the feature engineering, to design the features, and to transform what was the data that was acquired by our own senses in many aspects to a human palatable form. And this was very driven by what's called the language bias. So we had to define a language to describe the model. And we would end up with a space of solutions that is discrete. So it means that we have a space that we can move from one point to the other without any continuity. So this sort of representation, on the one hand, lacks smoothness. On the other, again, it needs a lot of human intervention and a lot of human resources, which is not very sustainable. So this is useful, it has been useful in many applications, but there were some problems. So for example, for digit classification, there was this 7-segment example. We had many times to, we could run this data set to test decision trees, SVMs, MLPs. Again, feature engineering, there was this human bottleneck. Knowledge was injected by humans, and it was hard to convey. So the difference started with the kind of approach where we could avoid the need for this human effort. So the famous MNIST example, images are presented raw, and the approaches like deep neural networks can learn the representation. So there is little engineering, so not completely without some engineering, and we can reach a level of artificial perception. So this learning representation really makes a difference and is something that can unblock and was very helpful in the process of unblocking AI. So AI is very much centered on machine learning these days. So I believe that in the future we will be needing other fields of artificial intelligence, not only machine learning, not only data science, and in particular in machine learning, not only these approaches that are more popular now. So what we have in blocking AI is, for example, in the search space, instead of a discrete search space that we had many times in the past, now we have a continuous search space that can give us much more interesting properties that allow the methods to be more easily successful. So the features are, instead of being engineered, they are raw. So we use pixels instead of features that have to be engineered by humans. We have now more optimal features instead of approximate features as we had in the past, because now we can fine-tune the process to look for the optimal features. And the features are also learned to fit the task. So instead of being the human deciding which are the features that can be used for this particular task, we can make the model learn which are the features that can be used. For example, in natural language processing or information retrieval, we had a vector representation like TF-IDF, which was coded from text, and this was already very powerful, and it still can be used to solve very important problems, and it's still used. There was tens of thousands of dimensions. It was sparse, it was stiff, it was not smooth. So what we have with neural approaches, for example, for natural language processing, is that we can use word embeddings and neural language models which are learned, not just coded. So we don't take a text and just transform the text into a a vector representation, as we do with TF-IDF, so it's not just coding, is learned as a task. So we learn the representations so that we can, for example, predict the next word in a sentence. Okay, so this makes a lot of sense, and it's a very different kind of approach that really makes the difference and helps boosting AI. So this does not require much engineering. Of course, there is some need of ingenuity to be able to set up the process that is able to learn this representation. Instead of having many dimensions, we can do a good job with just tens of dimensions, for example, or 1,000 dimensions. So for example, in TF-IDF, if we have a vocabulary of 30,000 words, we can have 30,000 dimensions. In word embeddings, we can do with 100, with 200, with 1,000. So this is dense. It's a dense representation. It's a continuous representation. It enables semantic inference, which means that the representation of words, for example, in this case, are closer in the space of representation if the words have similar meaning. Okay, so this makes a big difference. And we have now in NLP things like BERT, a neural language model, where we can make even better predictions. We can use this kind of models in very different NLP tasks. It is also, it works very well in different languages. And it is applicable to sequences, not only in natural language processing. So this kind of approach can be used to boost many applications in this area. In the area of recommendation, for example, there was a similar evolution. So we have a natural representation where a user A is defined in terms of the items that the user interacts with. Again, this is sparse. It is hard to relate, so it's hard to compare users. We have very sparse representations that give us difficult ways of comparing users. We can use traditional approaches like association rules, which have their problems, or more similarity-based approaches that are a little bit better, but still are close and very, very much tied to this kind of representation. And what made the difference here in terms of what can be very different in terms of results is matrix factorization, where again, we are able to learn the representation. So instead of being happy with the features that are given by the problem, we can produce a process that gives us the features that we want. And again, we can represent the data with a much smaller set of features, so it's low dimensional. We have optimal features, so the process learns the representation that is optimal for this particular problem. So this is a dense representation. It captures semantics, but it has this very small but important problem. It is unintelligible, so we don't understand, we cannot read what this representation is. And this applies to the result of matrix factorization in recommendation. This applies to word embeddings in NLP. This applies to deep learning in the features that are learned from the models. So this unintelligibility is something that comes with this representation learning more easily. And this is mostly what we lose with this kind of approach. So what is really making the difference here is that in one part we learn from raw data, so we don't have to feature engineer. We have smooth representation space. So similar objects have similar representation. Objects can be arbitrarily similar because we are in a continuous space, so there are no gaps. And this is very important for the smoothness. We have dense representations, which also have the advantage of requiring less space. We can have other things like a hierarchical structure of features, which is typical in deep learning. And learning instead of a discrete search task, can be done using optimization in a continuous space. And optimization from operational research field has also played a very important role in the development and in the boosting of artificial intelligence. So all the most important and the most successful tools in artificial intelligence, in machine learning these days, use optimization approaches like backpropagation. Even matrix factorization is solved with optimization approaches. Whereas in the past, artificial intelligence was based on more of discrete search or simply as using satisfiability. So we are dealing with incomplete information in an efficient way. So, learning representations is very important and is something that is very central to this success of AI. Of course, it is not everything, but the way that AI and machine learning moved from the features that we have to the features that are learned by learning the problem, have this problem of lack of transparency. So learned representations are for machines, not for humans. So they are built in order to make the process more successful in predicting something. But they are not readable. They are not made for humans. So can we get away with it? How can we try to overcome the problems of lack of transparency? So there is some very important movement on the importance of algorithmic transparency, on explainability. So explainable AI is a very hot topic, of having the human in the loop, which is related to these approaches and this problem. There can be different ways of attacking this problem, like, for example, combining symbolic and sub-symbolic approaches. This is something that comes from the past, but is, I believe, going to be more and more important in the future as we have to include more transparency in our models and in our artificial intelligence solutions. Things like Bayes networks and causality that have to be developed and have to be used in order to have models and solutions that can make sense for us humans. Okay, so what next? So what are the big things that we can expect from AI? And mostly in terms of research, but also in terms of what will be important for the companies and for economy and for society. So as you know, Europe is launching a strategy on artificial intelligence, and Portugal is part of this strategy, is also launching our own strategy for artificial intelligence. And the human-centric approach, the importance of the ethics in this process is very high. So we have to have human in the loop, human-centric AI. So this is something that researchers and also practitioners and companies will have to work on. So we need more, a better link between humans and machines. We will have more autonomous systems. We have some, but autonomy is something that is going to be more important in the future, and in particular, the importance of auto-ML, so the importance that we have to give to the ability of systems to learn how to do machine learning themselves. So they will have to be able to manage machine learning algorithms and even to come up with new machine learning tasks. So identify new machine learning tasks and make the system solve these machine learning tasks. Grounding is also very important. So this means that we can, for example, do natural language processing, but we don't have yet a good way of associating words with their meaning in the real world. So to really understand text, or at least to understand text to a level that is different from what we have now. Causality is also a very important topic. Green AI, which means that we have to be able to perform our algorithms, to run our algorithms and our systems with less energy. So there are very interesting developments. For example, there are neuromorphic chips being developed in places like the INL here in Braga and also in Lisbon, in Esqueman. And there are different approaches for these neuromorphic chips that can spend much less energy than the chips that we are using these days. Edge AI is also something very important, and being able to learn in devices and to run machine learning models in the devices, and instead of doing everything in the server, is also very important for intelligent environments and for autonomous environments like autonomous cars, for example. And that's it. Thank you very much. I hope you enjoyed the talk.